So we have learned some basic about data science. We learned how to use the pandas and the matplotlib to do some exploratory data analysis and do some quick visualization, do some pair charts. We also did some correlation heat maps. So all those are more or less preparing you to do to build a model. Pandas itself is another tool for building models. The tool that you want to use in Python is called Scikit-Learn. So this will be the tool that will be working pretty well for most of the applications. Unless you're dealing with a lot of data set, then you probably want to learn how to use a PyTorch, TensorFlow. That we'll cover on our last day of this workshop about how to use those frameworks to build neural networks. But for most of the data science projects, Scikit-Learn is more than enough for you to do some non-trivial work. Okay, so today we'll learn how to use Scikit-Learn to build the models. So you probably always hear about AI, machine learning, people put them together, or AI slash backslash slash machine learning or machine learning AI. But they are not equal to each other. Actually, if you're talking with computer scientists, they will tell you that AI actually is a superset, in the sense that AI is more general. It contains machine learning is just one area, research area inside AI in general. And if when we'll talk about deep learning tomorrow, but deep learning is actually a subset of machine learning itself. So all these methods put together is trying to build this. Ultimate goal is to build this artificial intelligence that can help us human beings to solve our help us with our daily tasks, and help solve some ultimate questions you may ask. Who knows? Now we are getting to a point. I know probably I heard a lot of philosophical questions asking. People asking experts about, will AI be replacing us? Are we just like kind of like experimental carbon-based supernatural being, just prepare for this silicon-based supernatural being in the future? Are we just part of the evolution, just like dinosaurs? And in the future, all the silicon-based supernatural being will be there. They have intelligence and dominate, our planet and dominate the universe in the future, because they don't even worry about the lifespan. They can just take on their backpack and just travel across galaxy and etc. But these are all the questions. It's not a question I think I can answer. Everyone has this opinion. This kind of question, since it's so hard to give an answer, so we have the freedom to think everything you might think about. So it's not a concern for me, at least. But based on my own understanding about what the current status of AI and machine learning are, it's still pretty mechanical. It's no intelligence there at all. Some people are concerned, but for myself, I don't concern at all. Technically, if you can train your model, as long as you can spend as much as you want, assuming someone pay you, right, to feed you, you can sit there and take all the training data and learn all the training data all by yourself, because everything we use to rewrite all the code to train machine learning models, those are in written languages, and those are in a given procedure. Assuming you can live forever, and you can learn what all the machine learning models are learning now, and learn what it can do, as long as you are good at bookkeeping, as long as you have sufficient time, you can do it. It's fully deterministic. There's nothing intelligent there. It's just the way how we do things, at least for now. There might be a point, when you train your model to a very complex structure, just like the example we talked about yesterday about graph analytics, right? It's starting from all the edges and the vertices. When you have a very complex structure and put all the things together, then there will be something fabulous coming up from them. AI might be something out from all the 0 and 1s, and you never know. But at least for now, I don't worry about it at all. There are people worrying about it, but I think it's probably too early, at least for now. Anyway, that's completely subjective. So that's not anything I want to convey through this workshop, but it's just some opinions I have about this AI and machine learning. Getting back to machine learning, since that's what's the topic, we are not going into robotics and all those kind of stuff that AI will be covering, and some other controlling and automation that's also part of AI research domain. But we are focusing on machine learning itself. At least for today, we are not getting into the deep learning part, but just the machine learning subtrunk deep learning. That's the part we are going to cover for today. So machine learning could be, there's people probably still continually adding new categories, but essentially, I think actually based on the current literature, there are three major types of machine learning algorithms. First one of them, First one of them is so-called supervised learning. That's when you have the data, also you have the ground truth about those data. You know what these data are, and when you train your model, you're trying to train a model to help you to do the mapping from the known data and the known results. For example, you have a picture, you know what this picture is. If someone gives you a picture, you know it's a cat, you label it. So when you train your model, you put this picture as well as this label in your training procedure, so that this training program will train the machine learning model, then it can tell if this picture is a dog or cat or other things. So similarly, when you're doing neural network, it's kind of similar. It doesn't need to be standard machine learning model. It could be a neural network. It can do something very similar. You need some input data with given labels. So the machine learning model, deep neural network can do the same thing. So deep neural network in many cases, actually a lot of deep neural network models we are using nowadays are supervised learning models. So there have been a lot of efforts to develop unsupervised learning models, like the transformer model or ChatGPT, and all the other fancy LLM models are based upon their actually unsupervised learning models. We're not getting into detail about those, but I can talk a little bit about those. I was hosting a workshop, I think last May or last October or November, I forgot. So we were talking about LLM and how you can use LLM for your research as well. So the last category is called reinforced machine learning. This one getting really popular lately. It's kind of interesting because almost all the language models that we are using nowadays, it's trained to use unsupervised learning. It just need to fit in the model a lot of well-organized text information, not like random text. It definitely won't work. So with well-organized text information, so the machine learning model, where is it? So the machine learning model can find a corresponding association among all the words. So you can, based on the association, and you can predict what the next word is. In most cases, that's the AI model we are dealing with. It's just predicting what the next words are, essentially. After you train your model long enough with sufficient number of data points, sufficient number of text information, your model will be able to predict the next words with more accuracy, higher accuracy, and with probably meeting certain criteria, and it shows a sign of intelligence. That's the LLM. But recently, probably heard about DeepSeek and some other latest development for when you are training these larger models. People are using reinforcement machine learning method to help automatically training this supervised learning method, so that you can unsupervised learning method, so that it will be more efficient, more effective. So the training cost could be reduced to probably 1/1000th of the original cost, or even sometimes even cheaper. And that will actually dramatically change the way how the the capital investment will be. People are probably not interested in investing a lot of money into OpenAI. Probably if you have a parameter a model with a similar performance, based on some benchmarks, of course, there are some industrial benchmarks you can measure the performance of different models. If the training cost is lower, that means it's cheaper to produce. It's kind of like it's a basic law in the free market. Whenever you get a place when you could get cheap product created with lower cost, the capital will go in there. So that's what the current trend is. Seems to be a combination of all the three, not just the supervised learning is also utilized in some of the latest training. So you can see this kind of all these methods and algorithms are actually combining together to provide the models that will be getting more and more intelligent, looks more intelligent. Reinforcement machine learning is mostly used in robotic training, but for supervised learning, this is more or less like a steps, procedures. You have basically two steps. Step one is training. Step two is called inferencing or testing, or if you can, simply could be just using or inferencing. It's the same. So when you are training your supervised machine learning model, you start with the training data, and we'll get into all different LM algorithms. But here, it's assuming it's like a blank box. In some cases, it's not blank, but it's actually for the machine learning algorithms we're talking about today. It's not a blank box; it's a white box. You can see what's inside. So that's the difference between neural network machine learning method and the standard traditional machine learning method. So today we'll be covering those methods that we can explain, we can understand. So with the machine learning algorithm, you can get your model trained, and also depending on the criteria you have, since I just mentioned that there are multiple industrial standard benchmarks, and there are many other built-in metrics you can use to measure the performance of your model. It could be simply just mean square error, mean square sum, and you can calculate which one gives you the lowest error. That's probably the easiest one. Or could it be the prediction of a given test data set? Ask you predict if this picture is it belongs to this particular category. If you make it correct, it gives you 1, otherwise 0. If you have 1,000 cases, you can easily calculate the percentage of accuracy based on that. So there are many ways to measure if your model is good or bad, right? So after a couple of testing, if your model is satisfying certain criteria, say 80% accuracy, it's probably good enough for many people. Some people probably, in certain cases, for some mission critical cases, you probably want 90%, 95%. So what do? You keep training, you get your model better and keep modifying your model. But in some cases, when you get to say 80%, it's probably good enough. Your model could be pulled out. You don't need to worry about the training data anymore. You can start using this model as a function for you to work on other things. So it should be supposed to be this kind of model after it's trained. You can just use it as a function, like a library, and then it can help you to make predictions. So this is essentially like 2 steps for supervised learning. No matter if you are using neural network or some other algorithms, it's still the same process. For neural network, this will definitely take much more time. And of course, if depending on the size of the data set, this could be very expensive. That's why NVIDIA stocks is shooting to the sky, mainly because everyone needs NVIDIA GPUs, because that will be much more efficient than just training on the CPU. You can do things that you cannot do with CPUs. With a GPU, you can speed up sometimes hundreds times. So for investment, if someone tell you get your money back in 1 year, another one tell you get your money back in 100 years, it's no brainer, right? People will put the money into the return with 1 year. So that's exactly why GPU is so hot recently. And I also mentioned AM system investing $45 million to purchase a GPU cluster, which is the latest GPU H200 GPU at the Raleigh campus. No, actually, it will be at the West Campus data center, not far from here. And everyone knows it's an opportunity to move to the next level of the research and engineering applications. So this is now we are getting to another category of machine learning algorithms. It's called unsupervised learning. Unsupervised learning means you have some data, you have no sense what they are, but as long as you observe here is a very, it doesn't need to be proactive. It could be passively observing. When someone passing by, you see it, you're observing. You're not going there, just poke around, right? That's different. Passive, active observing. Whenever you observe, you can have some impression or some information about the data you have. even though you don't know what they are. It's kind of weird scenario, but you might think about this. Consider you are going to an unknown planet, okay? You saw some animals or whatever you call it, anything, alien lives. Some of them are, rolling around. Some of them just walking. Some of them flying. It's kind of, you don't even need to know what they are. You don't need to know what they are. You can easily categorize them as flying objects, rolling objects, climbing objects, right? Crawling objects. And that's already doing categorization, that's already doing this classification. You are classifying those flying objects, flying alien lives as a group of objects. You don't know a name for it yet, but it doesn't matter. It's just like a Feynman, probably Richard Feynman, a very famous scientist. He once said, knowing a name doesn't mean anything. You need to know what they are, right? Someone can give you anything a name, but that's just a name. That's a symbol, a label. But you want to know what's really that thing is. That unsupervised learning here is mostly think about the intrinsic differences between all different groups or categories. It doesn't really matter if you give a name or not. At some point, if you stay on that planet longer enough, you probably give it a name automatically. You just say, okay, this flying over, just call this birds, right? Those rolling stuff, call it whatever. It's your choice. Whoever named it first will have the naming right for those things. So that's why I put it as class 1, 2, 3. You just simply give them index 1, 2, 3. It's your choice again. So label here doesn't really mean much. Now that's actually getting into another interesting discussion we had early this week. And the data scientists, we look at data and we try to, based on the features we collect, we put them into different groups. When you start giving them names, it's kind of comparable to giving some numbers, some units. After you start mapping these classes to some things you already know, you make association between your machine learning model to the knowledge, whatever knowledge you have been accumulating, or someone else in your team who is expert in a particular field. They can tell you, there's a first class is what, a second class is what. For example, you just ask me if I see a bird flying by, I don't know exactly the name, the scientific name for the bird, but I know it's a bird, right? But then if you get into details, if you have many data, I can probably see the difference between a big bird like ostrich and like sparrow. They're different to me. I can tell the difference. But when I first get started, I just know they are birds. They have wings and do other things. That's all I know. That's highly depending on the data set I have. If I have a lot of data set for different kinds, I'll learn it. I know all these birds are small with with this color, and they must belong to this group. Then gradually I'll learn more. That's exactly the process how we learn things, right? And then going to elementary school, middle school, high school, college, then you learn more and more because you'll be able to tell the difference between different categories, and then you'll learn deeper and deeper in the knowledge hierarchy, and your knowledge graph is growing, and then you have the capability to tell the differences. That's because we have been training our brains all the time, ever since we were elementary school kids. So a lot of analogies like that could be adopted in machine learning, and the models you train highly depending on the data you have. And for the unsupervised learning, no one tells what those data are. You have to learn all of this by yourself by trying to figure out intrinsic differences of the data types. So that's why this method actually a lot of people like this unsupervised learning method more because this one is more intrinsic. The other one, classification, even though I cannot say it's subjective, but how you label them, it's actually the right to label those different classes, groups are actually given to a group of people already define those terms. So you may argue differently, but that's basically what it is. If you look at these two kind of different problems from different perspectives. Reinforcement machine learning models, algorithms, you might think about a vacuum cleaner that can go around and clean the carpet all by itself. It's more or less like that. It doesn't have any preset data, be it unsupervised learning or unsupervised learning. You need the data. Either it's labeled or not. You need the data, pre-collected data there to train you. It's kind of like a book already written, or like a book of all the exercises that you need to take to learn. But here, it's starting from nothing. While you're moving around, you learn things. Every time you do something right, you get a bonus. You do something wrong, you get a penalty. Like keep doing this, you start picking up all the things. This is different learning system. I know I have 3 kids, and there's what's the name of there are different kind of learning systems. People are sending their kids to different daycares just for them to experience different learning styles. Some of school, daycares, they're just telling you that, hey, we just get kids explore. We don't teach them all the numbers and all the letters. We teach them a bit later, but let them explore. Let them to learn feel things. In Europe, a lot of daycares and elementary schools that do teach kids in this way. They just get them to the outside, let them explore, give them different toys, let them try. The teacher, so the teachers will just sitting there. Either, I'm not sure, probably they don't, read news on their phones, but they're just watching the kids, and the kids will be doing all the things they want. I never lived in Europe. I just watched some documentary, talking about those kind of different teaching methods. So that's more or less like robots. Again, it doesn't mean that you cannot train robots with no knowledge, but this is just one special way to train your robotics to be adaptive to the environment. Okay, if you are thinking about autonomous vehicles driving in an urban area, you need a prior knowledge. You need to understand the traffic signs, all those things. You need to teach. You need to train them that way. You cannot just simply send your car out there, just let it drive itself to learn. That's you can do it, but the police probably don't agree. Right? They will get your car and probably get you, put you in the jail. But if you're in the wide area, if here at Redis campus, there's a BCDC, Bush Combat Developed Complex. They design special terrains that put some UGVs, unmanned ground vehicles, on the ground. So let them just running around, detect all the terrains, slope, and other things. They don't train them, before, because they don't have the data there to train them. They want all the robots to learn all by themselves, to see how they can navigate around. Of course, sometimes they have GPS, sometimes there's a GPS denied condition, because it's a BCDC, right? So in that case, the robots needed to be learning itself. If it's learning fast, it's good. It learns how to navigate and do certain things. But if not, then it will take a long while for the robot to pick things up. But this is not a common algorithm that people in the machine learning community is doing. But again, if you are doing robotics, this is something you have to learn because it's getting to be really, really popular, because all the embedded computing devices are getting so powerful. This phone probably comparable to a supercomputer probably 20 years ago. A supercomputer, it cost like $1 billion. Now it's just this size. So the embedded device is getting powerful and powerful. You can do this learning much faster on using robots and using some embedded devices. So that's the last one. So now we are getting to the real meat of this course. It's just one slide, but it's all we needed to know about machine learning. At least in the context of this workshop, we don't need to get deeper to learn all the distribution, statistics. I don't think we have time in that. But superficially, what we are trying to do when we try to do machine learning is trying to find a function, literally a function that can map some input to the output. I'm talking mostly about supervised learning. For unsupervised learning, we'll get into that later on. But for supervised learning, you have input, which is your x, and y is your expected output. That's already measured. For a given x, the x here is a vector. Y here is a vector. For a given element of x, xi, this arbitrary x element I, and a corresponding yi, you should all the machine learning process is trying to do is find a approximation function. This function will never be accurate, 100% accurate, mainly because the data you have will be 100% containing errors. Otherwise, it's not real life data. Probably it's just fake data. For the real life data, you're almost guaranteed to have errors. So this function f will never be a pure mathematical function you might see in your math book. It'll be an approximation. So that's something you want to keep in your mind. You never get a 100% correct model unless you synthetic all the data yourself. That's a different story. Now, how to approximate this function f? We approximate it by minimizing my projected value based on my input data. That's this x is my input data. Subtract the output data y and absolute value. Here means more or less like you may literally think this is absolute value. I want to minimize the difference between my predicted output and my known output. So this turns this whole machine learning process as an optimization process. Optimization has been a very, very big field. Mathematicians, have been studying all the different kind of optimization problems for years and years. All they're trying to do is just doing this. You may take this whole thing as a function because y is a constant. After you get your data ready, both x and y, they are known. Those are known. Those are data. Those are numbers, right? This only unknown here is just this f. But the thing is, f is a function. How can you approximate a function, right? So we'll get into that. So for this function f, it could be in a very complicated format. It could be in a very simple form, like a polynomial. This f could be x plus b. That's a linear regression. This f could be x to a to the e to x power plus something. That's a exponential function, or it could be any other sine bx, whatever. You want to fix all those parameters. You can start by assuming certain function forms and then tweaking all the parameters you introduced. And this whole optimization process is trying to find those parameters can minimize this. It's not f itself, because f itself is very abstract. There's no such thing called a function that you can find. The function could be written in a certain format, could be parameterized, could be written in a nested function, could be in very, very all kinds of forms. But you can introduce those parameters and use those existing forms like x plus b, x squared, x to the third power, etc. Right? But those a, b, c, d, all those parameters are the things you really want to determine. Does that make sense? So there's no way you can get this f directly from this training process, because you only get numbers from this training, because that's numerical approach. There's no functional analysis in the training process. At least for now, no one is doing this functional analysis. That's mathematical analysis. It's not a numerical based machine learning training. So let me just repeat that. Given x and y, those are known for the given problem. You have your x. This could be x could be a collection of images. Y could be the labels. And you want to find this function to map this x to the y so that fx minus y is minimized. So the whole thing is trying to find this f. Okay. So there are some pretty common used symbols. These are almost the same. If you are reading, some online examples given by Scikit-Learn community and many other communities are sharing similar notation. It's kind of interesting. Almost all the Scikit-Learn examples are sharing the same notation. When you have a label, it's always y, lowercase y. Your input is always capital case X. In most cases, I'm not saying everyone is following this notation, but it's pretty common to have this notation. So X itself, consider X is a vector. If it's just one column data, consider if X is just time, Y is the measurements you have, then your X is just the time you're measuring. But X could be a vector, could be a matrix, or it could be a table, which contains multiple columns. Each column is a feature, and we call it feature and column. They are interchangeable in the context of machine learning. So feature extraction and feature engineering is more or less like finding the columns or redefine the columns that can help you to identify the properties of certain object you're studying. Right? Some of the features could be derived features. It's not simply just feature A or feature B you already have. Could be A column A times B column B will be your derived feature. Those features will be probably more relevant to your final output. So your function will be a function of A xi plus B, x2, x1 plus B x2. So that's called feature engineering. And when you try to find the corresponding features, can give you the best approximation for your final function approximation. So the model is written in this format. This is just simply in math. If you are familiar with math, it's called mapping from f function itself is nothing more than a mapping mathematically. In the modern math, it's mostly built on top of set, the definition of sets, right? This mapping is more or less mapping one set to another set. So the metrics here, the metrics is more or less like measurements of the evaluation model. This metric here is this error. This is the error definition of the error could be in many different formats. It could be simply the numerical error. If it's a regression model, then this is simply just numerical error, mean square errors, or just absolute value. You want to minimize that. If this is a fx itself is more like a distribution, then this difference could be the so-called difference between two distributions. That's called a KL distance. We'll probably get back to that a bit later, but we'll not worry about the distributions later. So there are multiple ways to define this metrics, and there are multiple metrics there. But essentially, it's just trying to minimize the error you might introduce using this f. Okay. So this is also, if you are learning machine learning, this is all you need to learn about the fundamental mathematics. If you want to go deeper, you can go very deep along this line. As people may talk about how to build a manifold, and all the weird mathematical terms all popping up if you start digging deeper and deeper into that. You're getting into category series, representation series, all kinds of weird stuff are popping up. So, actually, for the context of this workshop, this is probably already sufficient for you to get started. Understand all you're trying to do is find a function, and how to find a function, you parameterize it, then the finding function will be turned into finding those parameters. After you get the parameters fully determined through this minimization or optimization process, you're all done. Your model should be good. A pretty common practice for you do the training, when you collect a data set, this is a pretty common practice to divide your data sets into two parts: training data and testing data. Now, can someone tell me why? I know some of you probably already done machine learning. Why we need to do this? Why don't we just use all the data for training, and why we divided that into two parts?
You might end up training for something that, like, yes, it's common, but like it's not actually what you're looking for. So something like that's kind of related, or might be like, oh yeah, it's present in all the ones that are correct, just for no reason though. Like, or basically like you're overtraining it to something that you might not necessarily even know is what the correct thing you're looking for.
It's more or less like what you just said. Actually, I think I say 80% accurate about this question. The reason I think, getting back to my original question, why you want to divide this, is that you want to build up your confidence. You want to know for sure if your model is working or not. Now, assuming you're a student and I'm a teacher, I don't teach you anything. I just send you a book with 100 multi-choice problems. I hand it over to you. You learn all 100 problems. And then when I try to test you, I just pick one of those problems and try to test you. Will that be a good way to test? Many of you probably don't agree. It's definitely not a good way, because if the students learn hard enough, they can memorize every problem. They don't need to understand what's going on in the book. As long as they memorize the problem, it will be working. When you train a machine learning model, if you give all the data set to the model for the training, the model will, if you train the model hard enough, in many cases, the model actually can memorize something internally, because all the parameters will be tweaked so that all the data set will have some fingerprints inside of your model itself. With that, no matter what, as long as you put any testing problem from your data set, you're getting back to get a prediction, you'll get very accurate feedback. You might say, hey, my model is good, but actually in reality, you never know. Now you might say, okay, Dr. Tao, let's take this, say 100 problems and train that in data set. Let's take another problem for testing. Will that work? That's another very good question. Many people are asking me, if I use all my testing data set, and then all my data set for training, let's use 100 data points for training. Then you left asking the last thing, you have to go out somewhere to find some new data points, right? Why is that not a good idea? Yes, it's kind of like it's probably not a very good example, but it's kind of like you teach these students English and then test him Chinese. It's not that dramatic, but the data set you collect might be connected under certain conditions, under certain constraints. It's very, very hard for you to get the exact data set with the exact same condition and constraints you may have. By doing that, you're violating this kind of testing confidence. Whatever confidence you're testing should be using the data collected with a similar condition or constraints which you have, because it's very, very likely the same data set you have, they are collected by probably some group that with certain with certain constraints and with under certain conditions. But of course, it's always assumption. Given this data set, it's likely could be just combination of data collected by different groups. If you're using that kind of data set for training, what I said probably is not valid anymore. But in many cases, you're dealing with, for example, if you go out take some data set for some marine animals, in the ocean at this particular season, then the data set you have has a very unique constraint into it. So you are starting a small sample, but you don't want to introduce extra biases by using the different group of data for testing and testing your data, testing your model, because the data it's like using apples and compare with pears, right? It's just like not a good idea. But basically, you cannot build up your confidence. How do you know if it's because your model or because your data is from different collected under different conditions? Does it make sense? So this is an argument, that I think it's a pretty strong argument for you to do this splitting. This almost required process for you to do any machine learning model. If you go anywhere, anyone will tell you to do the splitting to make sure that you have some testing or validation set that after you get this model trained, you threw this away, not throw away, just put this away. Don't worry about this training data anymore, because the information inside of this part, green block, we already embedded into this training process, optimization process. Some function you're building is already knowing this part of information. Then you use this validation set data set, go back to check to see if you get 100% accuracy or 80%. That's how you get your confidence built up. Yeah, it's usually like 75, 25 or 80, 20. That's pretty common used. Some people I know that use like a 90, 10. But 80, 20 is pretty commonly used. 75, 25 is also depending on the data set, how big your data set is. If you don't have a so big data set, you probably want to use more for training. Otherwise, if you have 20 data points, how can you do this division if you don't have so many data points for training anyway? So it's highly depending on the number of data points you have. 75, 25, 80, 20 is a pretty common ratio for that. That's actually getting to one of my next slides. It's called a K-fold validation, because it's likely the way how you cut this probably change something, because it's accidental. You may accidentally pick this validation set has a completely different features as the other. It's completely possible. Anything is possible. This validation data set might be, when you divided it, if you even do the random shuffling, there's no guarantee that the training data set covers all the cases, and your validating sets might be containing. Those features might be completely separate, but this validating data set might contain something that training data set might not be containing. So in doing that, there will be so-called K-folding cross validation, and we'll get back into that. So there is the performance difference depending on how you divide the data, and so if you just do this not so carefully, if you don't try multiple partitioning, that's why usually it's pretty common to train this model multiple times by dividing this into different groups. You can do shuffling once and shuffling twice, and then to see how much difference you may have. So give you another layer of safety about the performance confidence. So again, these are pretty commonly used keywords. If you go to some examples, this underscore train is just like that's like 75% or 80% of the data you reserved for training, and underscore test, that's the data used for testing. That's almost everyone is using that, so that's a common practice. Now, y underscore predict, that's a predicted value. That's fx. That's when you, every time you get a model trained, the model could be trained multiple times. After you get it trained once, you can take that model, which is a function f, and apply your x to it. You can get a y underscore predict. So that's when you apply, when you try to apply your f on this x test, you get a y predict. That's your predicted value. That's this fx. That's when fx itself is something unknown, because when your f is not trained, you don't know what this fx is. But every time you got your model, every step, you do this multiple steps during the training, you can apply whatever f you have. It could be a very naive function, which might not be correct, but you can always get something predicted based on the f you have. So this y underscore predict is the predicted or expected value from your model. And what you do every time, you compare this y underscore predict to real y value for the given data set. Then you can see the difference. Okay. So this is a pretty commonly used representation for fx, more or less like that. So getting back to the cross validation, which is exactly the problem you just mentioned. If you do this dividing, how can you know if your model is good or not? So pretty commonly used technique is to take your data set and cut that into multiple pieces, and every time use one piece for testing, all the others for training. So you do this for everyone and find the best performance one, and the resulting model, the model is trained on the rest of the piece, and use that k. This k is a number, k. No matter how many big your data sets, your k could be 10, then you cut the data into 10 pieces. Each one contains 10%. Or k could be another number. In the extreme case, k could be equal to the number of data points you have. That means you only reserve one data point and use all the rest for training, and check the performance with the one you didn't use for training. You keep doing this for many, but again, this is not so efficient. That means you need to train your model so many times, k times, k minus 1, k times actually for every one. But you can keep, these are kind of like a parameter searching kind of, this kind of like hyperparameter. How you do the division here itself could be considered as this parameter. There's a ratio between your training data and testing data itself could be considered as hyperparameter. This could be affecting your performance of your model. So that's why people try different methods to find the optimal cutting here, or they can simply just cut data into multiple pieces and do that, and find the one with a optimal performance. So people have been trying a lot of crazy stuff, mainly because you don't have so many things to try. So this is you can always think about some ways like this to explore. Okay, cross validation is a pretty commonly used technique for checking the performance, and this K4 cross validation is supported by Scikit-Learn. Scikit-Learn provide a built-in functionality for you to do this very efficiently, very easily. So you don't need to worry about doing this. Scikit-Learn will do this automatically for you, and then you can just build a for loop and iterating through all the possible combinations. So again, this is a technique you may use in the future, but for this is not commonly used for deep learning, mainly because deep learning has so big data sets. They have different ways to do that validation for deep learning. This is usually used when you don't have a lot of data points, have very small data points. It's very likely when you just pick one data out, the rest of the data will be showing a dramatically different feature. That's when you want to be careful, right? So that's when you want to do a careful cross validation when you don't have so many data points, right? So what is Scikit-Learn? Scikit-Learn is the machine learning in Python. It will be implementing a lot of algorithms that we'll be talking about today, and it's providing a software framework to facilitate the process to find this f function. That's what Scikit-Learn is. It also has multiple built-in functionality for you to process that, like the splitting, like here. Not this careful. Careful is another one. It also provides a very easy way for you just need to provide a ratio. Scikit-Learn will randomly shuffle your data and then pick 80% of that and save that into a different group, which is not so hard to write a code about it, but Scikit-Learn has a utility to do this kind of work. So Scikit-Learn also has a special group of functions to help you do the so-called dimension reduction. We'll not get into the details, but we probably have a slide about it in a second. And the feature extraction and normalization for the data, because sometimes some columns have value all the way going from 100 to 1,000, right? Another column might have a value going from 0.1 to 0.2. So when you build up machine learning models, you don't want to have your parameters to have extreme different parameters. You want your parameters to be at probably similar level. So you want to normalize your columns to make sure your columns are always showing from 0 to 1 or 1 to 2. This is a pretty common technique to normalize your columns so that you can build a model with a parameter that are not so dramatically different for different columns. For example, if you want columns changing from 100 to 1,000, then the parameter needed to be very, very small to make it comparable to the other one. The other one needed to be very big, the parameter. I mean, the extra controlling parameter will be like a weight will be very big. So normalize your features or columns inside your data will reduce those potential numerical errors, and which sometimes it's kind of harder to detect and to identify. So it's a pretty common and recommended practice to do the normalization. Again, even for normalization, there are multiple ways to do it. You can do standard normalization, just more or less like a Gaussian-based normalization. You find the variance or standard deviation and find the mean, and if every value subtracts the mean divided by standard deviation. That's one way to do it. Another way is to find the maximum value and the mean value, and try to find the difference and divide every number by that difference. That's a mean-max normalization, and there are many others you can find on the Scikit-Learn website. Okay, so this is a Scikit-Learn website. As I'm probably mentioned previously, Scikit-Learn is such a wonderful toolkit. It's not only a tool; it's a community. This community provides documentations, tutorials, online tutorials. You can check out those videos tutorials as well. And also they have organized this website very nicely. If you want to learn a very specific type of method, just go to the scikit-learn.org website and get into the particular section. You can dig into almost all the possible algorithms you can find. So that's the beauty of this community. It's so vibrant and so dynamic. Every day you get some new updates. Someone will be sending a message to the to the maintainer to say, "Hey, I found this particular algorithm. Let's try to implement it." It's a very, very interesting community. And the primary purpose is just trying to provide a simple and efficient tools for predictive data analysis. So being able to easily understand the syntax is the primary design goal for Scikit-Learn. And it's accessible to everyone. It's free and open source, and it has a BSD license. If you want to build up some commercial software, you can use it. You don't need to pay any fees for that. It's open. That's a beauty about it. But of course, if you are using that for commercial software, then you need to make sure you keep the same license. You cannot modify license, but you can probably modify some of the code for your commercial. This depending on different open source license, so there are different constraints. But again, it's this one MIT and also Apache can allow commercial application, which actually greatly increase the user community because all those small companies are interested in using this as well. So it started as a Google Summer project by David Cornapier. I'm not sure. It sounds like a French last time. I believe he's a friend from France. It's starting as a Google Summer Code project in 2007, and later supported by a French Institute for Research in Computer Science and Automation. In RIA, it started supporting this project in 2010, and the very first version, 0.1 beta, which is like testing beta version. It's just very like a pilot demonstration. The very first public release was out in January 2010. That's when it was taken over by INRIA. So I just checked yesterday. The latest stable version is a 1.6.1. For most of open source projects, I'm not sure how many of you know what these numbers mean. The first number here is so-called major version number. Second number 6 here is called a minor version number. The last number here is called a patch number. So if it's a pretty common knowledge in the open source community. If, like the very first one, this is 0.1, where is it? 0.1 beta. So it's a zero major version, means it's not ready. When you have a real stable functional that product ready code, it's usually starting with a 1 point something. Whenever you see some code with a 0 as a major version, that means it might not be well tested. Just be careful, right? But it doesn't mean it's not usable. It's just like they cannot guarantee anything stable or quality control is probably much less. So 0.1, it's just like it's a first minor version, which is at a very early stage. Now, this means it has a major 1 version. The minor version already 6. Every time you have a major version jump from, say, 1 to 2, there will be some dramatic difference in the versions that there might be incompatibility in certain cases. If you are developing some code with 1 point something, and someone is not, then later on when everyone's using 2 point something, some of the code you are doing here might be thrown away. You won't be able to run your code right out of the box. So you need to make some modifications. So if you jump from major version, in a major version, that will mean some incompatibility will be introduced. But for the minor version, in most cases, they'll give you some warning messages. So starting from next major version, this function will not be usable. They will usually send you a warning message. But your code is still working. So minor version will not break the backward compatibility. The last one you don't really need to worry about. It's mostly about patches. Whenever there's a security problem, any other small typo errors here and there, these are just patches. That will not change the interfaces of the program. So that's basically 3 numbers. Even for this minor thing, you might tell that contains a lot of information. So that requires Python version 3.8. Python 2 is no longer supported by anymore, and so everyone now is switching to Python 3. And the latest version of Python, I think 3.14 or 13, I forgot. Probably 13. 14 is also probably out. 3.8 is a stable version that has been supported by the community for a while, and I think gradually you'll be bumping to next minor version. So all these versions actually matters a lot when you're doing this development, open source code development. You need to pay very detailed attention to all the versions, because sometimes when you develop code, and tomorrow when your friend is trying to use it, it might not be working because he might be using some old or newer version of the number. You have to make sure all the versions are matching, and so that you can guarantee the code can run out of the box. So to do that, Python has a peep. Some of you know, some of you don't know, it's fine. You can use a peep freeze to generate a list of required modules together with all the corresponding versions. So you can keep this file as a requirements.txt file. Next time when someone tries to install the virtual environment for the Python project, they just need to do pip-r requirements.txt. It will install all the version numbers, exactly matching the version number you need. So you can recreate exactly the same environment, so that you can avoid any non-necessary time-consuming, debugging, those kind of stuff. So virtual environment is a very, very important thing for Python. It actually helps a lot with the Python development. Even though you might not be counting the latest features and some versions, some particular module are providing, but you can ensure the stability for your code development. Otherwise, you'll be keep changing your code. If your code is depending on, say, 100 modules, it's possible. Sometimes some big project requires many Python modules. every day you'll see some changes here and there. It's very likely you'll be breaking, this new installation of the new upgraded version will break your code. You'll learn this gradually after you start doing those Python development. And this is a very, very nice algorithm map, and it's not only useful for us to learn how to use Scikit-Learn, but also useful for you to start doing machine learning in general. Someone asked me about number of data points. So how many data points are good to get started? See here, I told you there is a number called 50. It's like a magic number there. 50 is just, it's just a hand waving number, so no one can tell why it must be 50. Just, roughly, if you have less than 50 samples, go just get some more data points, right? If you have more than 50, then you depending on what kind of question, data science question you're asking for, then you'll be getting into different islands. Consider you have 4 islands, and these are like, some bridges and connected to all these islands. Every time, depending on your answer to the question here, you'll be shifted to different islands. So regression model is pretty common use. When you have a lot of data points, say more than 50, and you are not doing any categorical prediction, I don't want to tell if this thing belongs to this group, that thing belongs to that group. It's very likely I'm predicting something quantitatively. I want to predict the stock market, the value of the stock market. The value of certain stocks in the stock market. You are doing some quantitative prediction, so you're getting into regression model. Could be linear regression, could be logical regression, could be any regression model you're building. If you have less than 100 samples, you probably want to use so-called a statistical graded descent regressor. That we are not getting into details. That's when you don't have a lot of data points. You probably want to try that route. If you have a sufficient number of, if you have a lot of data points because it's so big, then the traditional way of doing the linear regression and least square will be too time consuming. So you probably want to use this method to find the corresponding regression model for you. Otherwise, if you have not so many data points, but of course way more than 50 data points, then you can try different regression models. Could be ordinary linear regression, rigid regression, there are supporting vector regression, all this kind of method. This is just one island. So today we'll talk a little bit about this classification and the clustering, but we'll not get into this dimension reduction. Probably we all have one slide about it, but it's mostly about to reduce the dimension of your multi-feature table into a smaller dimension by linearly combining all your different features together to form a smaller dimensional case. That's called a PCI, principal component analysis. Every time you do a PCI, more or less like projecting your high dimensional data into some lower dimensional surface. Then when you project like a 3D object into a 2D surface, you only see a shade, right? That's a 2D. Give me a ball, I project on surface, that's a 2D. That's one dimensional or dimensionless. When you can do the further, you can put for the 2D, you can put a line, it will project on that, it will become one dimensional. So every time you do the projection, you use a lower dimensional object to project the high dimensional object to the lower dimensional object, you get one dimensional reduced. You keep doing this, you can get to a lower dimension. Consider you have a 5-dimensional one, you do this, you can convert it, you can project that into 3-dimensional, 2-dimensional. Then you can do visualization. That's very important. A lot of analysis done for high dimensional data sets is through this first dimension reduction and then just pull it out. You can easily see the clustering behavior, other things. And okay, that's for dimension reduction. Let's see what time. Okay, about 1 hour now. Let's finish this diagram and then we can take a short break. For classification, if you are trying to predict if it belongs to a certain category and you already have the label, this category called a dog, that category called a cat, okay? Then you have a label, then you are doing classification problem. If not, if you don't have a label, it's just unsupervised learning. It's just a clustering, which is a clustering problem. You can put them based on the intrinsic properties of the data you have. They could be naturally forming clusters, but you don't have a label for them. It's fine. You know that they belong to a group because they're very alike based on certain criteria, and then you can put them together as clusters. That's how you do the clustering method. Mean shift, some of the k-means are pretty common used, and you can use a DB scan or other method. For classification method, if you have a lot of samples, very similar to regression model, you use statistic gradient descent method. This is a statistic gradient descent classifier, which is good for handling large data set in the traditional machine learning method. If you have deep neural network, none of this will be your worry. You just fit into your deep neural network and just try it and see if it's working or not. But this is like a classical machine learning. You need to understand the data structure first, and then you decide what kind of method you want to use. If it's less than this many data points, you can use a linear supporting vector machine and SVM. I'm sorry, this is a supporting vector classifier. And you can try different ones. So we'll get into some of the examples later. So this is another way to just, this is when I first learning Scikit-Learn, I tried to organize those things myself, trying to put together some nice, representation of all the different methods that Scikit-Learn is providing. You can divide those into like 6 groups, essentially. On the website, you see 6, but here the pre-processing, I'm not sure if it's showed up on the web page. Let me go back to check. It's the pre-processing. It didn't. Oh, it shows up here. So it is. So it has all everything. So it's essentially the same. The pre-processing part is a part that you usually don't go there to learn, but it's actually most important part for you to prepare your data, get your data ready, and for the model training process, for normalization, data splitting, and those kind of stuff. Will make your life much easier to get your data ready for fit into the training process. We'll talk about some examples in clustering, regression, classification, and dimension reduction. We probably have a PCA a little bit, a couple slides, but model selection is another advanced tool, because sometimes when you have a data set, you might want to try different models, different classification methods, not just one. Sometimes, I'm not sure if there's any, for a given problem data set, some particular classification method might be working pretty well, and for your data set, some might not be. So there are some intrinsic differences between all those different methods. So trying different methods might be a way to go. Another difference is about parameters for a given model, for a given algorithm. By changing those parameters, the performance will be different. And you can get into the details into the so-called grid search method, random search, etc. Okay, regression is something we all know pretty well. Even when you're doing experiments back in high schools, you are doing experiments, teacher will ask you to probably put out a ruler and draw the lines to do the best fitting for the curves. That's the easiest way to do the best fitting. As long as you can equally distribute all your points, on both sides of this straight line. This straight line is very likely to be the best fitting curve. Of course, you won't be able to get all the slopes and this, accurately, just like the model we are doing now numerically. You can calculate these numbers accurately. These 2 parameters can guarantee, both through this machine learning method or this, least square method, can guarantee the distance between all these points to my value, the total sum of that is minimized. So that's the machine learning model is minimizing. Basically, I want to minimize for the given point, given x, I predict a value in my fx, which is a value along this line. I subtract this the value I measured, and then I want to minimize the difference. So this whole process of finding these 2 numbers is an optimization process. This ax plus b, this is a function fx we are trying to looking for. And accidentally, since we are doing this linear regression, so this function is just a linear regression, relationship, x plus b in this format, because we are doing linear regression. That's why our fx is informed with ax plus b, and our job is to find a and b. After we get a and b fixed, ax plus b itself is a function that will fit my need. I found this fx. That's how I find my fx. Okay. It sounds like very abstract when you try to someone trying to find a function, but this is the function you're trying to find using least square method. And for different models, that you can try a different combination of these very basic functions, polynomials or sine, cosine. There are different ways to do this optimization, but essentially it's just least square will be working pretty well in most of the problems. So I think there's not much about this one. Everyone is familiar with regression, especially linear regression. We have been using this almost everywhere. In science and engineering, it's a mostly commonly used machine learning model to some extent. And linear regression is simply because this model is a linear relationship, ax plus b. So for the ordinary linear system, OSS, which is what's this? Ordinary linear least square. I'm sorry, ordinary least square. It's not least square. What this is why I put OLS here? It's in machine learning we simply call this linear regression, but in the statistics that separate from ordinary, ridge, and lasso. The main difference between all these three linear regression model is that the ordinary linear regression model is simply just trying to minimize the distance between the value y and the predicted value xw, and this w is simply just ax plus b, because this x itself is a vector. This is considered as a 1/2 vector, and y depending on how many columns you have. So this is the weights plus bias, which is a and b. A is a weight, b is a bias, right, for a linear model. So we are trying to find corresponding which is this is a w, omega w, to minimize this whole thing. X and y here are constant. You're trying to find a w to minimize this this value, which is L2 of this matrix. That's a mathematical formulation for this optimization problem, trying to minimize fx minus y, more or less like that. Now, for the second one, it's a little bit different. The major difference is that I not only want to minimize my errors, I also want to minimize something else. This something else is actually the absolute value or the length of my weights. I want my weights to not be shooting up, to a very big value. I want my w to get very, very small. And the process to do this cannot be zero, because when w can become zero, then this becomes trivial. It's not you won't be able to get a function figured out. So this w will never be zero, but it could be very, very small. Meanwhile, this error will be minimized. So it's minimize your error at the same time minimize your alpha. So minimize your weights, or your minimize your value for a and b. So you won't have very extreme values shooting up in your solution. This is commonly used when you have, as I mentioned before, when you have multiple features. Some features are strongly or sometimes strongly or not so strongly collinear with another feature. So if the correlation of these two features are greater than a certain value, this one will work well, because then you have a singularities in your matrix. If you have two parallel vectors in the same matrix, the rank of the matrix is actually one order less. You have a redundant vector sitting in your matrix, and then will make this value going. It's kind of harder to work for those kind of problems when you have a collinear vectors that you don't remove. But this can handle that by just reducing this weights for this collinear vectors, collinear features. So you don't need to do the feature engineering in this case. Otherwise, you need to go back to check your x vector to make sure all the X vectors, when you do this collinearity studies, like the one we did in the EDN, if there are two particular features that are very strongly correlated with each other, you cannot put them together in your feature. You have to remove one of them. That will work for ordinary linear regression, but you don't need to do that for rigid and also Lancer. Both are trying to minimize this kind of issues. Another big benefit for this kind of for this rigid and Lancer is that you are guaranteed to have some this special feature for overfitting, avoiding overfitting. When you do the overfitting, some of the errors showing up, and your weights and biases will be changing rapidly. But here, by minimizing them, you'll be getting yourself away from those rapid changes in your weights and biases. So again, these are all similar to the other regression model, but these extra features will make your linear regression model suitable for more general cases. So, there are some other similar processes you may look into, but these two are pretty commonly used method if you want to go one step beyond linear regression. Linear regression is very simple, very easy to explain. But if you have a more complicated features you want to study, then you want to look into those two, Lancer and rigid. So for regression model, one of the pretty commonly seen feature, it's not just for regression model, it's for many other models. We'll talk about those later. But for the given model, this, the true function, which is, since this is just a toy model. In reality, you don't know the true function. But here we know this function, like a green curve, basically is what we are expecting. And the samples you have is all in all the blue dots. Okay. For the given data set, like all the blue dots, the best fitting actually are shown here as a blue curve, which is actually almost overlapping with the true function here. So this is like ideal case. This is when you've done everything perfectly fine, well, you get this prediction. You get your value. You get the curve figured out, which is matching your data set well, and also it covers everything. It's an ideal case. Now, if this is like underfitted case, in the sense that when you try to study the structure, using some functions, since your parameter here is not many, for the linear curve, is only have ax plus b, a and b. By tweaking a and b, you won't be able to match all these features because this is like a high order term. This is more or less like a second order, third order polynomial or some other shape. I don't know. But this linear curve definitely will not be representing these variations pretty well. You cannot capture a lot of nonlinear features because this is only a linear term, right? Of course, this is just one single example. Even if you have a nonlinear term, sometimes you won't be able to match this nonlinear perfectly because you have some other issues here. So this is so-called underfitting because you are missing a lot of features without, not capturing all the variations in your data set. Now this, and also in this case, you'll have a pretty big error. If you take all this there, you put them together, it seems that the error is pretty big. But this one will have a very small error, training error, which actually definitely will be better as a model to predict the values in between or somewhere beyond. This function itself will be a good function. Now let's get into the next example. This one is called overfitting, in the sense that your blue curve is trying to passing through every blue dots here. If you simply evaluate the training error, this one could be very, very small. The reason it's very small because your blue curve is passing through almost all the dots. But look at this curve. By passing through all the small dots, you have to change your function structure a lot. And this function might be rapidly varying, even though it's matching pretty well with all the dots you have, but its function itself it's not a very good approximation function for the green curve here. This is called overfitting. Overfitting always happens when your training error is very small and almost zero, but your test error is getting pretty big because some testing data set randomly you pick along this line, as long as you're not those 20 data points, there could be resulting a very, very different value than the green curve should have. This one is of course, it's always bad, no matter what. You have a very bad training data set, your training error is also big. If you look at training error, this, when you're trying to calculate the difference between your expected value and the true value, the training error is pretty big. This one's training value is a training error is very, very small, but the validation value is very big. That's when you just have the overfitting problem. So we'll take a look at how the training curve looks like later on. You'll see the difference between the training curve and validation curve. So training curve always started with a very big error, gradually decreasing. But at some point, if you keep training, it will shooting up again. The validation error is starting with a very very small accuracy. I would say validation error starting with again with a small big error, and then when you get in training, it's getting slowly, and then it start picking up. Oh, I'm sorry, that's for validation error will pick up. But when training error, if you keep training, it will keep going all the way, getting slower, getting lower and lower. That's for the training error. But the validation error will have this interesting, like a V shape. Okay. So next we'll look into some examples. I think we have time for, hopefully, I'm sorry, we should have time for some examples on the Jupyter Notebook today, but we'll need to probably move a little bit faster. So the classification is a method for you to find, for your model to be trained on some data with a given label. So here you can easily see I have 4 groups, which is already labeled. I already know which type belongs to what. So I give a different colors representing the different type. So I know this is probably cat, dog, whatever. You can name it whatever. Now someone give you a new point, like the red dot here. Then it's your model's job to tell me which class this one belongs to. Now, if you look at this visually, it seems to me, this is very close to this green cluster. It should belong to this one, right? It's technically, actually, depending on the data, this might be the case. You might be right. So this dot might belong to this one because the distance between this one to all the other data points are getting closer. And also, if you look at the distance, this one might be actually, if you calculate total distance, might be closer to this as well, depending on how you measure the distance. So the distance is actually a very, very important thing when you start doing clustering or classification. It's a very important. And this distance is not necessarily the length. It could be any dimension, and it could be any unit. So supporting vector machine is it's a method that can deal with regression, clustering, and also classification, which is a very special technique that could be used to do all this. So the essential idea is to find the corresponding separation boundary line, can divide your data into 2 parts. This line could be a straight line, could be a curved line, but in general cases, supporting vector machine can deal with this long linear data. So in general, it's a curve, and through some transformation, you can probably consider that as a way to do a very clear cutting into your data set into 2 parts. So essentially, it's trying to find this curve that can divide your data into 2 parts, and the distance between each part of data to this curve could be maximized in the sense that the minimum distance, this is so-called a supporting vector machine. This small tiny vector is so-called a supporting vector. Kind of like you squeeze this, squeeze the curve on both sides as close as possible to the curve you want to do a separation, and this small vector is trying to support this separation between 2 types of data set. So you're trying to find the curve that can maximize the separation between two groups of data set. And this could be a straight line, could be a curve. So that's what a supporting vector machine can do. So supporting vector machine can do the division. This more or less like all the curves you can draw with supporting vector machine by taking this different chunk of data and with different linear kernels. And we'll get into some examples later on, but just assuming with different functions, this different shape could be drawn, even given the same data. If you look at the data, the same data set with different kernels, which is like different function format. Either I use sine, cosine, or x or x squared. Those are like the kernels I want to use. But again, these are just different kernels. I just want to, for example, I want to use those x squared and x plus y, b, etc. as example. But with different kernels, you can draw different shapes of that. And each with different kernel, the shape will be looking different. But no matter what, in each case, this division is trying to maximize the separation between all the groups in either case, because the fundamental basic functions are different. That's why this shape are looking different. But it's trying to do its best with its given function shape to maximize the separation between two different groups. So each one is using a different kernel. Oh, this one is using also, this is a linear kernel, this is a linear kernel. This is a polynomial kernel. This is a radiation boundary. I forgot the B. What's it? RBF. I forgot the abbreviation for this RBF. It's a separate. It's a different function. So this can handle nonlinear cases. That's where you see this shape boundaries are not just straight lines. But for linear cases, you have a straight line separating these boundaries. It's essentially a way for you to divide your domain into different areas. And then you can, whenever someone gives you a new point, if it falls into this area, I can label this white. If it falls into this area, label it blue. Okay. So we're not getting into the mathematical details. It's just too much for today. So clustering is a little bit different. Clustering, you don't need to do a lot of training. It's in many clustering methods, it's more or less like an algorithm. It's like a rule you set and follow. It's not like a training process when you try to optimize certain things or minimize a certain function. Okay, let's try to figure out how all the data got collected. If you look clearly on this one, you can easily see there are 3 patterns here, 3 clusters here. But even though I put 2 labels, but you can consider this like a 3 blobs or 3 clusters. But the number of blobs here I'm defined might be wrong here. But for this one, you can see is that you can see it's either 1, 2, 3, or it could be 1, 2. A very big cluster, small cluster, etc. So visually, you can already have some feeling about how these clusters are working based on the scattered plots. K-means algorithm, it's a very commonly used algorithm for doing clustering. Essentially, when you get started, all the data points, you have no idea what they are or how they're labeled. But based on these are randomly labeled data points. You don't know, not labeled. You don't have any labels for clustering. Those are just data points I randomly put together. So you don't know what they are, but what you started by randomly pick 4 clusters. This is like a randomly pick the 4 clusters, assuming I want to have 4 clusters. So that's a parameter which K is referring to. If you say it's a 2 means cluster, that means you're assuming this group has 2 clusters to get started. And this K will not change. So that's the tricky part. So when you start doing this K-mean analysis, cluster analysis, you have to take some visualization to see how many clusters you really want to decide. Then you're trying to find the center of the clusters for you. But before you specify K, this algorithm won't work. You have to tell me what your expected K is. If it's 3, you're trying to find 3 clusters. If it's 4, trying to find 4 clusters, which is kind of interesting, but where to define clusters, but it is what it is. So what it does, if you define this K for 3 or 4, say for 4 in this case, it will randomly divide your data into 4 groups, and then use this initial separation to calculate the mean value of the distance. Assuming this is like x and y, you can use that as a coordinate to find the mean value. It simply is the average of all your x and average of your y value for this particular group. You find the corresponding center.
You do this for all the data points, okay? And then for each data point, you calculate the nearest, what's the next one? The number of cluster, it's for each data point, for each center, you calculate the distance between all the points to you and try to see if there's another neighboring point, give you the more, I'm thinking that's the mean. Oh, after you get the mean value calculated, and then you calculate the distance between this point to all the other points to see if the distance is getting closer or shorter. If not, you move it to the new data points. You keep doing this kind of shifting until at some point you convert to 4 points that the value will not be changing anymore. So this is called k-means square. The mean means every time you do the mean value for the x and y, you keep shifting that so that you minimize the distance between this one or all the other points inside your cluster you're assigning to. Right? So that's the k-mean method. I think we should have a. Let me go to, okay, this slide should be before this. That's why I feel like I missed something. Another pretty commonly used, is there a question here? Is there a question? Or? No. Another pretty commonly used classification method is the nearest neighbor. This one is also an algorithm. It's not something you need to train. So for this classification, it's conceptually very, very straightforward. You define the k nearest neighbors. That's number k is your definition. You can say, let's define k equals to 3. And then, assuming this green dot is your new data point, you want to predict which cluster it belongs to. And all the red blocks and triangles, these are existing data. You have 2 classes already. You know them, and you have them in your data set. So now what you do, you start from your point, you put a small radius around it, draw a circle around it, and then you count. If you have k here, if it's 3, if you have 3 numbers of one type of number, if you count inside this circle, solid circle, you only have 2 triangles and 1 square. That means, well, I don't belong to any neighbor. It's not. I don't belong to any class. Next thing you do, you enlarge your circle, make it bigger in the dashed line, and then you start counting again to see how many triangles or how many squares. Now, if you continue counting, you look at this dashed circle. You find that you have 1, 2, 3 squares, but only 2 triangles here. Since my method is called 3 nearest, k is a parameter you need to set. If it's 3 nearest neighbors, whenever you find when you gradually enlarge your circle, when you start reaching the nearest neighbor of 3 nearest neighbors of the same type, you will label yourself as a square. Okay. Another Chinese saying, 近朱者赤，近墨者黑. How to translate him? And when you're getting close to bad guy, you're bad. When you're getting to good guy, you're good. Right? It's kind of similar. So if you give yourself a number, whenever you get to the circle, then when you start getting birds in a flock flying together, is that an American saying? The birds in the same flock flying together. I forgot. Let's see. But yeah, it's kind of like that. So when you find your neighbors are more likely to be this, then you just turn yourself into. This is an algorithm. This is not a training or minimization. Anyone can do this. And this turns out to be the most effective and efficient way to do classification in a traditional machine learning method. And it doesn't require a lot of computation. It works pretty well. This is a pretty common way to do the classification. The catch here, you need to define the distance. The distance sometimes is a tricky thing. How can you define this distance? If you just physically distribute it, it's kind of easy. Just calculate the coordinates and get the distance calculated. But if you're in an abstract space, define this distance actually itself is tricky because how you define the weights for different dimension, and it's not an easy task. But you can always start with Cartesian, whichever numerical value you're using, after you normalize them, you can simply calculate the corresponding value, and then you can get started. It's better than nothing. Actually, so you can start doing something with this k-nearest neighbors classifier. So again, this is how computer scientists doing clustering and classifying before deep neural network coming. But this does not work for images. It's just so hard for them to do the images for classification, which is something we can easily learn actually with a machine learning, with a deep neural network. The image classification is almost trivial, and we can get it back to. So let's try some simple examples with the first exercise here. So the book I'm referring to here is there are actually two books. One of them is called Hands-on Machine Learning with Scikit-Learn, Keras TensorFlow. That's actually I have some examples actually borrowed from this one. And the other one is called Python Data Science Handbook, which is also a pretty useful book. You might be able to find this PDF files online and for the first edition, but I'm not sure about the second edition. Okay. So for k-means, this is the method I just mentioned. This is the correct k-means method. If you have this cluster, you find the three. You start with the three centers. You can keep doing the averaging and find the minimum distance between this same data point. And then you keep doing that. Then your center will be converging to the point where all the center will appear. So. This is basically the answer. I can probably select a number of clusters that you think the optimal number. That's why you need to do the EDA. That's why EDA is something so important. For you to estimate there's a good number k, it's better to plot it out so that you can roughly see how many clusters you may have. And then you can initialize k points as a centroid. So randomly pick k points in your cluster as a centroid of all the clusters. So each cluster has a center. That's called a centroid of the different cluster. And then attribute each observation to its closest centroid. You can, for given data points, for this data point, I try to calculate my distance between my current data points to this, and to this. Which one is the nearest? I enable myself to be his type. So it's like if a farmer, living near the kingdom of one king, you claim yourself to be his citizen or whatever, kind of like that. And then after you get that done, you calculate the mean of all the labeled data points for the central. If it's usually be shifted a little bit, this will be shifted somewhere here, this will shift it here. Then gradually, after all this shifting stops moving, all of the central stops moving, then you are converting to the point that you are getting to the number of clusters you are trying to find, and all your centroids are the locations become the center of your cluster. So these are some examples. You started with this distribution. This distribution, if you are familiar with this one, is actually the three normal distribution. This one's it's at 0, 0 with a standard deviation 0.8 along x and y. This one is mean is distributed along the x is 2, y minus 1, which is here, this center, mean, 2 and minus 1. This is 2 and minus 1. That's another center. So I created 3 clusters with this method called make blobs. That's a very easy way to start some testing problem with Scikit-Learn. So you can create these blobs and starting your analysis. You don't need to get real world data. This dummy data will be working for you just for testing purpose. So you run this shape and then you import this k-mean. And these are the only function calls you need to use k-mean. You define the k-mean and give the number of clusters equals 3. That's because I guess it's 3. And then you do the fit, and then you get that model train. The model will be saved into this k-model object. This object will contain all the weights and biases, etc., for you to make predictions. And then this will print out the centers of the 3 of all the 3 centroids. So beauty is that for this object-oriented programming, after you get a model trained, all the required information will be stored under this object as a given attributes, so you can easily print them out. So this it can only be calculated by iterating through all this data you have, and then it will try to find the convergent centroids of the three clusters. These are the centers of the clusters. So this will print a corresponding label. So it'll give you this will based on the classification, you'll print out label 0, 1, 2, 0, 1, 2, etc. So it's for your model. So it's already doing the clustering for you. So your every data point in your array will be labeled with the corresponding cluster. This one is trying to do some scatter plot. This is ground truth. This is a cluster. Actually, it's very similar, or it might be a little bit different, but it's very close to each other. Because the ground truth is corrected with some randomness. So this center calculator might not be exactly the same because there are some random numbers getting into the picture. Also, if you see there are some points are mislabeled, but that's what's expected. Even if you don't know this ground truth, it's very likely for you to classify all these purple points as this blue one because it's just so close to this center, to this cluster. Right? So that's why what you see is actually showing to the right here. That's the predicted output, which is everything close to this cluster center will be labeled as that. But in the left here, you see there are some mixture areas that has a mixed values. But there's no way that you can tell this difference because your method can only based on the distance, and the points falling in this range won't be able to label as other one. So iris dataset, I think we'll have one example. We'll skip this iris dataset example. We'll get into this one later on. And then there's a more customer example. It's a very common example. So it's on the gender, age, and also annual income and the spending score. Of course, if you are working in a mall, you definitely want people with a higher score, spending score, so they want to spend more money, right? You'll make more money. And this is trying to drop the gender. We just try to do this neutral analysis, try to just look at the age. This airborne method is trying to find I'll not get into detail. What airborne method is trying to do the k-mean square k-cluster method. But the thing is, how do you know if your number of classes is correct? So this airborne method is trying to see which one gives you maximum benefit without, when you're getting more and more clusters, it's still working. The error is getting smaller, but the actual benefit you're getting is getting less because the errors you're introducing or getting, the gain is less. So when you're going from 2 to 3 to 4, for example, for 4 here, this is probably that's where the error ball happens. Probably 3 seems to be where your error ball is. That's your switch point. If you turn this into this way, this is the one gives you a minimum. But if you look at this shape, this error ball point gives you the maximum benefit without you going to 4, but your performance of getting less, it's getting starting level up. So this is like the turning point, like a switch point. That's so-called error ball method or knee method. If you turn it around, if you're going this way, it will be like a knee method. If it goes this way, consider you put your error ball down. This is where your error ball happens. This is the point you want to pick for your cluster. So that's how you do the hyperparameter tweaking by trying out all the possible clusters. When you do the clustering and calculate the error. This is, I think, this so-called what's this error? Anyway, this is just one way to evaluate error here. You'll get that later on. But this one, this 3 will give you the maximum benefit. That's where this error ball happens. That's where you want to set your number of classes equals 3. So that's how you tweak your number of classes systematically. It's not just widely casing, right? If you don't do any visualization, this is the way how you pick your cluster. Okay, there are some other methods. I'll switch this. I'll skip this one and go to the next interesting example. We have this is Scikit-Learn is trying to do some. I think this color compression, more or less like a reduced order modeling. We have an image here. I'm not sure this. I thought I got this one from another professor I'm working with. So this is image processing already. So what we are trying to do here, we try to find the cluster center of. No, actually, it's not a. It's kind of like a dimension reduction, but actually we are trying to do the clustering of the color spread around this image. Okay. No. So this original image, this is the 16 color image. It's just trying to find the corresponding color that can, doing the color clustering, but removing all the, we are using only the picked color at the center and removing all the other details from this image. By doing that, we'll reduce the size of that image a lot. So let's don't worry about this one. Let's go to the next example in the slide deck. We have 10 more minutes, which is should be fine. Let's leave. So PCA is a method for you to the PCA is a method for you to find the principal component in your data set. If someone give you this data, it's a clear to everyone. This is like has a linear dependency from your X and Y have some linear dependency. There's strong correlation along this direction. If you just look at the data perspective, actually, if you think your center is here, along this direction, that's where your maximum variance happens. That's where you have a maximum variance. Along this direction, you have a second maximum variance. That's the direction. You have second maximum variance. So these two directions are considered by PCI principal component analysis as two major directions. This is this is the major direction with a maximum variance. This is a minor direction with a variance, but since it's a two-dimensional, so it's the only next component we may have. So you can find the major components of this distribution using these two vectors. So this will be the major axis, it's a minor axis. So PCA is trying to find this vector and this vector. And using these two vectors, you can construct the data, and using the whole method here is called a reduced order, the dimension reduction method. And then let me see if this is the one example to do a so-called PCA. So what we started is start by this this logo. When I started working at a defined visualization, which now is not there anymore. We are converted into a college, but I just try to show what we can do with this kind of PCA here. Okay. You'll see what I'm. So this is the original image. As I mentioned, this image is nothing more than a matrix. Every image is just two-dimensional. It's just a matrix. Since this is a color image, it has RGB, a red, green, and blue, 3 channels. It's just like a stacked 3 layers of a 2D matrix, and that's it. Nothing more, nothing less. So if you just look at the dimension here, it's just 300x and 250, 44 along Y direction. If you check the mode here, it just shows you what kind of, at RGBA, it has 4 channels. What's a opacity? That's what's this A is transparent. I forgot this alpha. I'm sorry. Alpha is more or less measuring the opacity or transparency. RGB, red, green, blue, and transparency. Because this is a PNG file, it has this extra transparency that you can use. So this is like image information. So what I'm trying to do here, I convert this 3 channel into a gray channel. There is a given formulation that if you are familiar with image processing, it's just like a weighted average of these 3 numbers, RGB channel. And then you can convert this into just 1 channel. That means I now have only a 2-dimensional matrix, no more extra layers, just 1 layer, 2-dimensional matrix. That's my image. Okay. Oh, okay, this is extremely small. So what I resize it, probably cannot even see it. Now what I'm trying to do, I resize this image into like 1/12 of the original size. That's actually tiny thing. It's actually still the matrix. So next, I'm trying to convert this matrix into a dimension, into a 12 by 15 matrix. This is what it looks like. That's a logo, still the logo here. Of course, you cannot see it because it's getting so small. I converted it into so small, but it's a matrix representing his logo. I'm just trying to, the reason I want to make it so small so that I can print it out. You can easily see it as an ASCII format. That's the department visualization, whatever is at the top is a Pakistan logo, but it's a highly downsampled image. Each number here representing the number. I already do the subtraction of this 255, so this more or less like the downsampled logo here. So this is when we resize the back, this is what we have. It's just so blurry because we lost a lot of information when we do the downsampling, right? That's a brutal force downsampling. Usually that's not something you want. Because when you're compressing the image, doing all this, you are gradually reducing the resolution, you lose a lot of information. So let's reload the image and make sure, this is a grayscale image. I converted it into grayscale, and that's original size. And it's about 300, 250, 44. And the shape, I just turn that into the array. This is pretty big. I don't want to print it out. It's all, put out a lot of numbers. So if we turn this NumPy array into image, this is what we see. By turning the NumPy array into image, that's actually converts back to the original image we have. So what are we trying to do here? This is the hour. Not sure why do I have this. I should do. No, this is just doing the addition. I'm sorry, this is not what matters. What matters here. This one I'm trying to, last one, I'm trying to do the PCA here. This is just a plot the PCA. Don't worry about details. Okay. If I do the decomposition of this matrix. This is a one-dimensional data I have. With one-dimensional data, one component, just one vector. I can reconstruct this image. It doesn't lack much. I only have one vector representing this whole 300 and 244 matrix. It's I lost a lot of information. With only two components, I roughly see this structure there. With three components, three vectors. Instead of 300 vectors, I have three vectors here. With four vectors, I can reconstruct about 85% of the image. With totally 9 images, 9 components, I can reconstruct 97.6%. It's a dramatically change of the size, even though, it's still very small compared to the original image, but with only 9 vectors. Principal component, each component is more or less like a vector. With this 9 vector, I can reconstruct this here, mainly because each vector is capturing one of the main features inside this image. And with top 9 vectors, I can reconstruct the image like this. This is used a lot by information compression and compression algorithms. But again, this is not a 100% lossless. This is like so-called a lossy compression because I lose some information. I lost about 3 or 4% of data there. But anyway, so that's the PCA. You can make this probably more. 49, let's say 5. We should have 2 more minutes, which is good. Now, with 25 components, you can get 99.59%, which is already very much like the original one. Compared to the original 300 and 200 times 244, this 25 vectors will be already good enough. So lastly, I want to show this example, but I think it's already there. You all probably, some of you already tried it, but we have some time to go through this linear regression model that are probably already tried in the first where's how can I run this? Okay. I load all the modules needed to do the very simple regression. The model is as simple as a linear regression, starting imported from Scikit-Learn linear models, a linear model. So what I do, I first create a line. This is the dots I created with 3x plus 2 plus some random number. That's my dot. That's my as testing data. Okay. So next, this is one. Yeah, I plot it out, and then I print out the shape. Here is just 20 points along x, and 20 points along y, and then this is the model. How you use Scikit-Learn to do the modeling. You create an empty linear regression model, and then you fit it with x and y, and then you can get a model trained. Then you can print out the coefficients of the model, which is simply the x plus b. I believe why this one is showing. Oh, this is a a. This is the x plus b. This is the b. So remember, the original data was created with 3 times x plus 2, right? If you look at the coefficient, we have a 3 times 3, which is a, 1.979, which is b. You can reconstruct the model here. You can, with this interpretation, you can roughly estimate the determinant of this r square is about 97%, 98%, which is pretty good. You can do the model prediction. This shows you the model and as well as the original data set you have. So you can do this for nonlinear model as well. This time I'm trying to create a y, which is x to the 4th power plus x to the 2nd power, etc., plus some random variables. But when I try to do the regression model, I create 4 vectors. Each one is a nonlinear term, x squared, x cubed to the x4th power. I do a multilinear regression. This is what I got, which matches the original set pretty well. So this is a SVN, supporting vector machines. Again, this is how to make a blob of the testing data set. This is what I mean by kernels. As you just use different kernels to define your supporting vector classifier. This is a classifier. You can build up your model. And this is your SVC to separate your two groups. That's your supporting vector. I'm sorry, this is a line dividing the supporting vector. So you can try different ones, but all the beauty about this one is that the function, the way how you call the function, and the feature function is almost identical for all different methods. After you get a model constructed with some parameters, you can just do the fit, put x and y, you get a model fitted, and then you can use this for prediction. So the predict function is almost everywhere. Fit function is almost everywhere for all the models, and it's very easy. After you learn how to use one, by using another model, it will be straightforward. You can do the same thing for the clustering, and you can do the k-means, which is exactly the same. As you can see, you start by defining a k-mean with number of clusters, and then do the fit, and then just you can output the cluster, and you can plot out the scattered plots and see the difference. Finally, this is an example with the PCA. We have the iris data set. This one is trying to find the major axis and the minor axis for the clusters. So even though it's not well, this PCA might not be needed, but it's definitely help you to see what PCA is doing for different type of iris flowers. So again, Scikit-Learn is a really, really powerful tool. It contains almost all the standard machine learning methods you may need for your research project. For the deep neural network that we'll be learning tomorrow, we will not get into the details about all the methods, but deep neural network is more about how to train your neural network and build your neural network. But today, the Scikit-Learn algorithm is more like a rule-based. You need to understand what you want to do. And it's either based on the algorithm itself or based on some linear analysis. And so with that, I think that's all for today's workshop. Any questions? This ECE and computer science are teaching this machine learning for one semester. So I'm compressing this into 2 hours. Again, it's very condensed materials, but I think we covered some basic concepts. All these materials and all these are kind of like providing the swimming pool. You need to go in there and swim. We already have a handbook, but you need to jump in the pool and swim, right?